Great, thanks, thanks Bernard and Philip and all the organizers of this summer school. I love coming to these summer schools. It's basically one of my favorite things to do as an academic. It's just fun. I actually attended a summer school when I was a grad student. And, you know, all the people I was playing volleyball with and having a good time with, not all of them, but some of them ended up being very famous, and I learned a lot from them. And it was just a lot of fun to learn from people. So, okay, following from Chris's brilliant lectures, I'm going to talk about probabilistic modeling and Bayesian inference. So I missed Chris's lectures from yesterday. I don't think I will overlap hugely, but if you seem bored, please close your eyes and look like you're napping, and then I will know that I should either make a loud noise or, you know, go faster or do something different, okay? So probabilistic modeling and Bayesian inference, this is what I love to do, so I should be happy to talk about it here, right? Certainly happier than sitting there working through 1,400 NIPS submissions, which is what I've been doing for the last 5 months. What is machine learning? Well, you know, the name keeps changing. It's been around for half a century, actually, probably more. It's got a lot of different names depending on, you know, who you talk to. You know, if you want to get a job these days, you probably are better off calling yourself a data scientist or something like that. But wait a couple of weeks and there'll be probably another name. You know, but that's not the point. The point isn't the name. The interesting thing about machine learning is that it's a field that is very interdisciplinary. It relates to lots of people from different communities trying to understand how to build systems that learn and how biological systems learn. So, you know, fields like engineering, computer science, obviously statistics, cognitive science, psychology, computational neuroscience, even fields like economics are doing things that are relevant to machine learning. So as machine learning researchers, we can learn from all of these different people, and at a cocktail party, we can have interesting conversations with people in all of these different fields. Okay? So, the interesting thing about that is not that there are many different people with very, you know, incongruous views of what learning is, but actually that over the decades, the same set of ideas and mathematical tools have been reinvented by lots of people in lots of different fields, as Chris was saying, for example, with the Kalman filter and the hidden Markov model is just one example of that. And so machine learning as a field brings together some of the mathematical foundations and practical applications of systems that learn, reason, and act. Okay? Now, there are to caricature a little bit, there are different ways of thinking about machine learning. One of them is, it's a long list, it's sort of a toolkit of different methods that we have for processing data. So you feed your data into some sort of algorithm, out come some answers, and then you choose methods that have either good theoretical properties or empirical performance, and ultimately we're interested in making decisions and predictions from data. What I'm going to talk about is the view of machine learning as a sort of you could think of it as a science of learning models from data. So the view of machine learning I'm going to talk about is not necessarily the majority view of machine learning, although Chris has also been describing a very similar viewpoint on how to build learning systems. But it's an interesting kind of way of trying to build up machine learning systems from some sort of first principles. So essentially, those first principles involve defining a space of possible models, learning the parameters and structure of those models from data, and then making predictions and decisions. Okay, so it's a modeling view of machine learning. So what do I mean by that? Well, what's a model? Okay, so the term model is used by lots of people in lots of different fields. Certainly in the sciences, you know, you have models of the, I don't know, certain biological processes. In astrophysics, you have models. So what is a model anyway? What's a climate model? What's any kind of model? Well, a model is fundamentally some sort of description of possible data one could observe. Okay? Because if a model can't say something about possible data, then there's no way to know if it's a good model or not. Okay? So if a model is a description of possible data one could observe, then the probabilistic view of modeling is the following. It says, let's use the mathematics of probability theory to express all the forms of uncertainty that we have in our model, and all the kinds of noise and anything that we don't know for sure, anything that could be random or unknown. Random and unknown are actually quite different things, okay? So we're going to use the mathematics of probability theory to represent uncertainty in just the same way as, you know, we use the mathematics of calculus to represent rates of change, okay? Then the nice thing about this is that those same rules of probability theory can be used to infer unknown quantities, adapt our models, make predictions, and learn from data. And up until about 100 years ago, this used to be called just probability theory, or even sometimes maybe inverse probability, where you were looking at, given the data, what can you infer about your unknowns. That was inverse probability. And then at some point, the term Bayesian got invented, actually by a frequentist who started using that term to kind of make people who did inverse probability seem like they're following some kind of cult. I think it's worked. So even 100 years later, you know, Bayesians seem like some sort of cult. But what I would want to argue with you is, you know, we're no more Bayesians for using probability theory than most of you are Newtonians for using calculus. Okay? So we're going to use probability theory. And, you know, here is an image of, who is this? Okay, anybody? You think I'm joking? Sorry? Oh, very clever. I know why you got into this summer school. Okay. No, well, you're wrong, and I'm wrong. Actually, we've been using this image for decades to represent Thomas Bayes. But it turns out that an expert in, Reverend Thomas Bayes was nonconformist minister in the 1700s, and somebody who's an expert on how nonconformist ministers dress. Okay, nobody in this room is an expert on that, right? But somebody who's an expert, a historian, has looked at this image and told us, unfortunately, that this is with great certainty not Reverend Thomas Bayes. Okay? Because a nonconformist did not wear this kind of clothes. But anyway, we're going to keep using his, you know, whoever this guy is. Okay, we're going to keep using his image to you know, refer to Bayes. Okay, but what we do know, well, actually, there's some doubt on that as well, because there's a posthumous paper written by Richard Price. But anyway, after Thomas Bayes died, he published a paper where he had a rule. You know, if we were also lucky, he published a paper where he had a rule, which I'm going to paraphrase like this. He didn't use these exact equations. It's a rule for turning priors on hypotheses. So, in other words, what you know about hypotheses before you observe data through something which is just a statement about what your hypothesis predicts about data. This is supposed to be your probabilistic model, part of your probabilistic model, because it's supposed to make predictions about data, and we're going to use the calculus of probability for that. So you turn the prior over the hypotheses, what you knew before observing the data, into the posterior, which is what you know about the hypotheses after observing the data. Tells us how to do inference about hypotheses from data, which is nice, and learning and prediction can be seen as forms of application of this rule. So this is the really nice thing, but actually Bayes' rule is not an axiom that we start with. It gets even simpler than that, okay? So here's the plan. What I'm going to do in this lecture, I have basically 3 lecture slots, and I have 2 longish lectures, so at some point I will break when the clock ticks or whatever, and we'll move on to the next thing. Probably lunch, I guess. In my lectures, what I'm going to do is, in the first longish lecture, I'm going to introduce the foundations of Bayesian inference, then talk about some of the problems of intractability. I'm going to give you a whirlwind tour of approximation methods, sort of like 2 slides on each thing that could, cover like a PhD thesis, basically. And then, I'll have some time for discussion, some fun things about, Bayesians and frequentists and how we can all be happy and live happily together and so on. And then in the next lecture, what I'll do is I will kind of give you a flavor, because, this is an advanced machine learning summer school. You don't want to just learn, Bayes' rule for 3 hours or something like that, right? I'll give you a flavor for some of the kind of fun and interesting things that we're doing in Bayesian nonparametric research. Now, I will be doing this without going into a huge amount of detail, because Yi-Wai Tay in the second week will have some lectures where he will cover Bayesian nonparametrics in much greater detail, and other lectures on, for example, Gaussian processes by, I think, Philip Hennig as well. Okay, so this is the plan. This is the more detailed plan. Do you really want to look at that? No. Okay. Okay, let's start from some basics. Okay, this is like the bread and butter of machine learning. These are the kinds of things that we do for a living. I would say probably 90% of like applied machine learning is classification. Okay, so let me just talk about classification, then I'll talk about regression, then I'll talk about clustering. You better all know something about this, right? But I'll talk about them because we're going to see how to formulate these in a probabilistic framework. So very quickly, here is linear classification. You have data, pairs of x's and y's. X's, let's say they live in some real d-dimensional space. Let's say y's are binary classes, class labels, so plus and minus 1, represented by crosses and O's here. Okay, so the key ingredients of any machine learning problem are data, some sort of model of some kind, and some kind of goal. Okay, so the data I've told you about, these crosses and O's. Here's the simplest model we could come up with for classification. It says the probability of the class being +1, given some parameters and the input location, is determined by a line. Okay, so if you're on one side of the line, this is just a fancy way of writing down, you're on one side of this line, you are probability 1 in class 1, otherwise you're in class -1. Okay, this is a hard binary classifier. You can soften it afterwards if you want. And now, what do we notice about this model? Well, the model has some parameters. Okay, these parameters theta that determine the decision boundary, this green dashed line. So those are the parameters. There are d plus 1 of them. So what's the goal of learning? Well, the goal is to infer these parameters from the data, presumably so as to predict future labels of new data points. Okay? And probabilistically, we would state that as predict the future labels, the probability of the y given the data that you've observed, d, and an input location, x. All right, that's linear classification. Let's talk about regression. So now our data is pairs of x's and y's. Okay, x's and y's, look at these red dots. X is on this axis, y is on that axis. And we want to fit some sort of regression curve, not a regression line. So let's fit a polynomial curve. Okay, so here is an expression for an mth order polynomial. And of course, we don't really expect our polynomial to go exactly through all our data points. So we're going to have a noise term here. And we have to make some assumptions. Well, let's make our noise be Gaussian. Just, like we made a hard linear assumption last time. Here we make a Gaussian assumption just as an example. We can, of course, do other assumptions. It doesn't matter for this point here. So we have a model. And now, what are the parameters of the model? Well, the parameters of the model are the coefficients of the polynomial and also that noise standard deviation. Okay? And what's our goal? Well, our goal is to infer these parameters from the data so as to predict future outputs given new inputs. Same goal as before. Now, a more complicated example. This is clustering with Gaussian mixtures. Now, Gaussian mixtures can be used just both for clustering data, and they can be used for density estimation as well. Okay? So what's the data? This is what we would call maybe an unsupervised learning problem. We don't have x and y's, we just have x's. Okay? So the data are these points in d-dimensional space. They're n data points, and in this image here, the points are these little blue dots. And, there are lots of these little blue dots. N is large here or something like that. Okay? Now, what's our model? Our model is that the x's came from some Gaussian mixture model. Okay, we have a second pointer. Okay. Ooh, also green. Okay. I'm going to do something brave. No, green is good. It just eats the battery. That's what's bad. Okay, let's see if that works. Amazing. Okay. All right. So our model here is a Gaussian mixture model that says our data comes from a mixture of m components. These are the mixing weights, the sort of fraction of data captured by each component. The components are drawn as these ellipses. Okay, there are 6 of them in this picture. And each component is a multivariate Gaussian density, just like Chris described. The multivariate Gaussian density has some mean, mu, and some covariance matrix, sigma, and that's drawn as a 1 standard deviation ellipse in this picture. Okay? So again, we have ingredients, data, model. Model has parameters. The parameters are the means and the covariance matrices of each of our m Gaussians and our mixing proportions. And our goal is to infer the parameters from the data. Maybe we want to predict the density of a new data point. And we want to infer maybe other things like, do 2 data points, does, say this data point and that data point, do they belong to the same cluster or not, for if you're doing clustering? Okay, any questions about that? Yes? Okay, a Gaussian mixture. Okay, I'm going to ask some questions. Do you know what a Gaussian is? Okay, good. Do you know what a multivariate Gaussian is? A Gaussian in more than 1 dimension. Okay, so drawn here in 2 dimensions. A Gaussian mixture is a way of modeling complicated distributions by adding together these Gaussian bumps. Okay, so I have 6 Gaussian bumps. I've added them up together with some weights, and that's exactly what a Gaussian mixture is. You look happy. Good. All right. Excellent. All right. So this is our 3rd model, and those are the goals. All right. So Well, what's the point? Well, we had three kind of very different things, classification, regression, and clustering with Gaussian mixtures, but it's all about inferring parameters from data under some model. Well, how do we do that? And here's the good news. We don't need to know very much. We don't even need to have much memory. We just have to, when in doubt, appeal to the two basic rules of probability theory. Okay? So what are the two basic rules? I think maybe raise your hand if Chris covered this already. Okay, good. The two basic rules are the sum rule and the product rule. So I won't go into them in more detail, just to say that Bayes' rule follows from the sum rule and the product rule just by rearranging some terms. Okay? And here I've just rewritten Bayes' rule. Instead of with x's and y's, I've written it with thetas, d's, and m's to evoke the idea that we're learning parameter models theta from data d of some model m. Okay? And that's basically it. Now, of course, the sum rule, if a variable is continuous, turns into an integral. So we're all happy with that. I don't even really understand what integrals are. They're just tiny, tiny sums. I've decided I don't believe in real numbers. Real numbers are not real. That could be because I'm lacking sleep. Anyway. But, you know, we'll use this funny sum. This is also, they're both sigmas, by the way. The sum is like a sigma, and this is also like an S. So they're the same thing. It's true. This is where these symbols come from. Okay, so now what do we do with Bayes' rule? Well, we're interested in doing prediction. Okay, so we're going to have to invent some magical method to do prediction. Right? No. We just look at the sum rule and the product rule. And that tells us how to do prediction. So how do we want to do prediction? Well, we're trying to predict something unknown, like a new data point or any quantity of interest, x, given the data that we've observed and the model that we've assumed. Okay? So, so what does this tell us? The sum rule says that if we were to sum over theta, okay, that's the sum rule, we could add in theta and sum it out again. All right? And the product rule, oops, this is when, sorry, I have a wonky power supply. Okay, great. I shouldn't be chewing on my power cord late at night, even if I have to do 1,400 NIPS papers. It's probably not healthy. Okay, so the prediction rule basically says, what does it say? It says integrate or sum over all possible parameter values the predictions of that you get from those parameter values. So this is just the predicted distribution over x that you got from that particular parameter value. For all of those models I showed you before, that's something easy to compute. Where the weights of that integral are given by the posterior distribution over your parameters given the data. So prediction in a Bayesian application of the sum rule and the product rule is naturally an ensembling method. You ensemble over all possible parameters weighted by their posterior. Okay, that's the thing I'm showing in green in all of these slides. Okay? Now, what about model comparison? Well, you know, is a third-order polynomial better than a fourth-order polynomial? Should I have a mixture of 5 Gaussians or 7 Gaussians or Gaussians at all or t-distributions maybe? You know, we all have lots of model comparison questions if we do machine learning, probably because there's so many models out there. So for model comparison, we just apply the sum rule and the product rule at one level higher in the hierarchy. Okay? And this term in red, which I keep highlighting in red, is what's called the marginal likelihood. This is the probability of the data under our model. That's the integral of the likelihood integrated with respect to the prior. Okay? And this term ends up being very interesting, and I talk about it a little more later. All right, now, where is the optimization rule? Okay? There is no optimization rule in probability theory. What are you guys doing studying optimization? No, it's very useful. I love optimization. Optimization is absolutely great, but it's not part of inference. Okay, it's not part of probabilistic inference. From the kind of purist Bayesian point of view, optimization is part of decision theory. Once you do all the manipulation of uncertainties, then at some point somebody puts a gun to your head and says, "All right, is it a cat or a dog?" Okay, you know, and then you have to make a decision, and that's when you apply optimization theory. So I do lots of optimization theory, especially when people put guns to my head. But it's not one of the basic rules of probability theory. Okay, so so that's model comparison. All right, just so we're all on the same page, here is learning a Gaussian the hard way. All right, so you have Bayes rule here. What am I talking about? Well, I'm talking about, let's imagine we have our data here. Our model is a multivariate Gaussian. The data are the blue dots, and the parameters of this thing are the mean vector and the covariance matrix of the Gaussian. And this, in particular, is a pretty bad model of that data, right? The Gaussian is nowhere near where the data is. Okay. So traditionally, we would be, you know, a lot of people think, okay, let's optimize theta to fit the data well. Oops, maybe we'll overfit. Let's regularize it. Let's do some other funny stuff. You know, if you just forget about that, you just say, well, the Gaussian has a mean and covariance that I didn't know in advance, so I need to represent my uncertainty and my lack of knowledge somehow. I'm going to use probability theory for that. Then I observe the data, and then I have a posterior distribution over the mean and the covariance matrix. Okay, any questions about that? Okay. So this is a boring example, and thankfully machine learning has moved well beyond learning a Gaussian. Okay. But ultimately, that's all you need to know, okay, from this kind of probabilistic framework. All right. Is it lunchtime yet? No. Okay. Okay, so I lied a little bit. There is more. Otherwise, you know, we wouldn't have jobs, right? You know, I couldn't be, you know, a professor if that's all I knew, right? You know, or at least I hope my colleagues don't realize that's all I know. All right. So, so where does this all come from? Okay, well, you know, all right, I told you about the sum rule and the product rule. Well, that seems a bit boring, right? Is there more that motivates the Bayesian framework, you know? Where does the prior come from? Everybody's uncomfortable about that. You know, even I'm sometimes uncomfortable about that. Not really, you know, I've gotten to terms with it now. But, you know, where does the prior come from? Where, you know, how do we come up with priors? And then there are these integrals, you know. I don't know how, I learned optimization for 3 semesters. I don't know how to do integrals. How do we do integrals, okay? So these are the things I'm going to talk about for most of the rest of this lecture. Okay, so what motivates the Bayesian framework? Let's step back a little bit and let's think about some fun problems. This is the kind of thing I was interested in when I was 14, and I thought that was what I was going to work on for my career. I guess I'm not totally far off. I can still use these images in my slides, but I certainly don't build these kinds of things. Okay, so let's think about building something like this. Let's not think about the hardware aspects of it. That's too difficult. Let's think about building the brain, that easy part. Okay, so consider a robot. We want our robot to behave intelligently. Okay, And, you know, we think that, you know, there are different schools of philosophy about that. Some people build robots out of rubber bands and they don't think about representing beliefs and things like that. But imagine we want our robot to represent beliefs about propositions in the world, okay? Like, you know, whether something coming at it is hostile or not, or whether its battery level is low, or whatever, okay? So the robot needs to represent beliefs. So what are we going to use to represent beliefs? Well, you know, logic is a good candidate, okay? We could start with logic. Things are either true or false. That seems a little, you know, difficult to do everything just purely with logic. So what we'd really like is something that represents strength of belief, okay? So we want to represent these strengths of belief numerically in the brain of the robot. And now we ask ourselves a question that for now seems totally unrelated to statistics or machine learning. How do we represent strengths of belief in the brain of the robot numerically? So we're going to represent strength of belief in some proposition X as B of X, okay? It's a strength of belief or plausibility of proposition X. And, you know, we could say, all right, I'm gonna arbitrarily rescale strength of belief so that 0 means the robot believes something is definitely not true, and 1 means it definitely is true. So the extremes recover logic. And we also extend our symbols, kind of, you know, you might get a premonition here about what's going to happen. We extend our symbols so that B of X given Y represents the strength of belief that X is true given that we know Y is true. All right? So now people have thought about this for, you know, over 60 years. And there's an interesting way of thinking about this, which, you know, people call basically the Cox axioms at this point, which says, essentially, if we think a little bit about how to represent these strengths of beliefs, and we come up with certain axioms, like strength of belief or degree of plausibility is represented by some real numbers between 0 and 1. And then we have some basic qualitative correspondence with common sense, which I'm not going to go through. And we have some basic consistency requirements, like, for example, if a conclusion can be reasoned in several ways, then each way should lead to the same answer. So if I process, you know, if I know 3 things, then it shouldn't matter in my rules of manipulation what order I process them in. I should get the same strength of beliefs at the end. And moreover, the robot must always take into account all relevant evidence. So we can't arbitrarily say, I know 3 things, but I'm going to flip a coin and arbitrarily forget one of those things if the coin comes out head. That's also not allowed, okay? So I must use everything I know. And then equivalent states of knowledge must be represented by equivalent plausibility assignments. So we can't basically end up with multiple possible assignments for the same things. I'm not going into this in great detail, but basically, if we accept these Cox axioms, then there is a nice consequence, which is that belief functions, which I've just described here, must satisfy the rules of probability theory, including the sum rule, the product rule, and therefore Bayesian, the Bayes rule. Okay? So now we get a derivation of probability theory as a way of representing beliefs, which is very nice. Okay, it's not about repeatable experiments. Now I can say things like, you know, what is the probability that, you know, the US will have a military intervention in Syria over the next week, okay? That's not a, you know, thankfully, that's not a classical repeatable experiment for which I can compute frequencies. Next week only happens once. When I say that I'm talking about my strength of belief, you might have different probabilities. Now, we shouldn't feel uncomfortable. What this is saying is we shouldn't feel uncomfortable about using the word probability to talk about that, because that's exactly, according to the Cox axioms, a good use of the word probability. Okay? All right, so this is one way in which probability theory can be formalized as a calculus for representing beliefs. Well, what about if we are like, oh, okay, beliefs, who cares about beliefs? I'm a gambling man, you know, what can you tell me that would be relevant to me? Well, for the gamblers out in the audience, or maybe the economists, or the kind of stock market traders, well, here's something you might care about. If you're willing to accept bets according to your strengths of belief, what that means is, just to be precise, if you're willing to accept bets with odds proportional to the strength of your belief. So let's say your strength of your belief is 0.9 in something. That means that implies that you will accept a bet that will, when X is true, it will gain you, say, $2. When X is false, you will lose $9. So that's a way of kind of calibrating what strength of belief means. Okay? If that's the case, then unless your beliefs satisfy the rules of probability theory, including Bayes' rule, then there is a set of bets that you are willing to accept such that you are guaranteed to lose money no matter what the outcome. Okay? That's a bad thing. It's not that you're expected to lose money. It's like somebody is going to cheat you out of money. It's like pure arbitrage. All right? So the only way to guard against Dutch books is to ensure that your beliefs are coherent with respect to the rules of probability. So if we want our robot to make decisions about how it navigates, then probability theory might be a good, you know, thing that it would use for decision making as well. Otherwise, some other robot could cheat it out of its pocket money or something. All right? So now, you know, you might be concerned and you might say, well, you know, I've learned about frequentist statistics and I don't really like all this stuff being so different. So is it all that different? Well, here's a couple things that might help. So this is called asymptotic certainty. What I'm going to talk about here, I'm going to sketch some theory without being very theoretical about it. Okay, but if you want to read the sort of you know, formal proofs, you can go and find them in the literature. Okay, so assume you have some data set D sub n consisting of n data points. And now we're going to assume that it was generated from some true parameters theta star out there. Okay? Then what's going to happen if we do Bayesian inference? Well, under some regularity conditions, and the regularity conditions matter, okay, so for example, your theta should be finite dimensional, not infinite dimensional, and in general, you know, you want your model to be identifiable, okay? Then under such sort of regularity conditions, as long as you put positive probability density on theta star. In fact, it's a little bit more than that. You should put positive probability mass around theta star, in a little ball around theta star. Okay? What does that mean in English? Okay? You can't say theta star was impossible under your prior. If you say theta star was impossible under your prior, okay, then no matter how much data you observe, what's going to happen? Theta star was impossible, okay? So, you know, if you think that it's impossible that aliens will land on Earth, even when the aliens, the little green men, are tickling you in your bathtub or whatever, you will still believe that aliens are, you know, are not going to be, you know, you'll believe they're not aliens, right? Okay. Okay, so as long as you say that theta star was possible under your prior, then in the limit, your posterior will converge to a delta function around theta star. Okay, so you'll recover the truth. I mean, that's sort of a good thing, right? You know, we'd like theories that recover the truth. Of course, we might care much more about rates of convergence to that, and that's much more involved to study. Now, what happens in the unrealizable case, so where the data was generated from some p star of x, some true distribution, which cannot be modeled by any theta, okay? So let's say your data comes from a, you know, complicated mixture of 3 t distributions, that's the true distribution, and your model is a multivariate Gaussian. Okay, so you're stupid, you just chose a multivariate Gaussian model, and you get infinite amounts of data. What's going to happen then? Well, you know, then your posterior will converge under some regularity conditions to a delta function around theta hat. Okay, what's theta hat? Well, theta hat is the theta that minimizes the KL divergence between the true distribution, the true data distribution, and the distribution predicted by that likelihood function. So the probability of x given theta. Okay. So what is the theta hat that minimizes that KL divergence? Well, let's write down the KL divergence. This is an expression for the Kullback-Leibler divergence, a measure of distance between probability distributions. The theta hat that minimizes that is what we would normally call the maximum likelihood theta. Okay, it's the theta that maximizes the likelihood as a function of the parameters. Okay, so in the unrealizable case, you'll converge to the maximum likelihood. Okay, any questions about that? All right, so now let's talk about asymptotic consensus. Okay, so one of the funny things about Bayesian methods is that you can start from different priors. Oh, that's not actually funny. You know, all modeling starts with some assumptions, and all modelers can come at problems with different assumptions. Bayesians just represent those assumptions in terms of priors. Okay, so what happens if you have two Bayesians with different priors? Okay, Bayesian 1 has some prior, Bayesian 2 has a different prior. All right, and now let's consider what happens when they observe the same data D. All right, now this is important. Assume both Bayesians agree on the set of possible and impossible values of theta. Okay, so that is the set where this guy 1 gives positive probability is the same as a set where that guy gives positive probability. Okay? Now, if that's the case, then in the limit, as n goes to infinity, the posteriors, P1 of theta and P2 of theta, given the data, will converge to the same thing. Okay? So if two Bayesians, you know, all right. So, you know, to come up with a nice intuitive example, if two Bayesians agree on, let's consider an example where this fails, okay? Let's say, you know, one Bayesian puts probability mass on God existing of 1, and another Bayesian puts probability mass on God not existing of 1. These two don't satisfy this criterion. Now, no matter how much evidence they observe of, like, you know, some miracles happening or whatever, you know, astronomical evidence or whatever evidence you can imagine, they will never agree in the end, right? Okay, so that's a case where this fails, but as long as they kind of put 0.99 and 0.01 and 0.01 and 0.99, then in theory, if they both live infinitely long, you know, that's the sort of issue with asymptopia, right? You know, things have to go on infinitely long. In theory, they'll converge to the same beliefs. Okay? All right. So I'm going to skip. There's a very simple demo of this, but I'm going to skip that because there's more fun things coming up. Okay. All right. So, so here is your first exercise. All right. That's what I meant by fun things I get to watch while you suffer. Consider a binary variable. Okay, that could be something like rain or no rain, or heads or tails for a bent coin. Everybody has pencil and paper out? You think I'm kidding? Okay, x is 1 or 0. Okay, so let's model the observations D using a Bernoulli distribution. Okay, so this is a representation of a Bernoulli distribution. The nth coin toss has some probability q of coming out 1 and probability 1 minus q of coming out 0. All right? So first of all, first question, is this a sensible model? Let's say for the weather. Anybody? Yeah, it seems a silly model for the weather. You know, if you have like a big cloud over you for a week, then you might get rain for multiple days in a row or something like that. It's not, the events are not independent across days. So it's not a sensible model for the weather. It might be a sensible model for a bent coin, maybe, as long as you don't flip the coin enough times that you kind of damage the physics of the coin or something. Okay, so so that was the easy question. Okay, do we have any other choices? Well, of course we have other choices. Yeah, anytime we write down a model, we always have other choices of other models. Okay, now we're going to do an exercise. All right, to learn the model parameters, we need to start with a prior and condition on the observed data. For example, I'm going to choose the easiest thing I could think of. I'm going to start with a uniform prior. That prior is 1 for all q's between 0 and 1. That one looks like... There's chalk somewhere? Here. I really didn't have to draw the uniform distribution for you, did I? Okay, 0, 1, it goes up to 1. Okay, that's your prior. Okay, now, what is the posterior after observing x1 equals 1? So the way I want you to do this is talk to the person sitting next to you, okay? And you have 2 minutes. Okay, raise your hand if you think you know the answer. Oh, okay, I'll give you another 2 minutes. Do you think you know the answer? Sorry? Sorry, this is, okay. Let's stop, all right? Who has questions about my question? You have a question about my question. A meta question. Yes. Yes. Indeed. Is this a question or is it an answer? Okay. All right. Let's let me get somebody else to give an answer. Okay. I want somebody in the last 3 rows. Okay. You're the lucky man. Go for it. Sorry? Yeah, that's a very fancy answer. Can somebody give me a answer for dummies? I'm not saying that you're wrong. Okay. Okay, somebody in this half of the room. Not sitting in the front row. All right, how do we even compute this, okay? Well, you know, I'm stupid. I don't remember anything, but I remember the sum rule and the product rule. So we just apply the sum rule and the product rule. Okay, this is what we have to turn the words into what I meant. Okay, so this is what I meant. The posterior over Q given x1 equals 1. The posterior is, this thing is proportional to the prior times the likelihood, okay? The prior was this thing here. It was just 1. Okay, this thing is just 1. But it's constrained to be between 0 and 1, right? So what is this likelihood? Sorry? Q. Okay. So we get really very advanced mathematics here. 1 times Q equals Q. Okay, but notice I said proportional to, all right? So why is it proportional to? Because it integrates, you were pointing out, it has to integrate to 1, okay? So there is a constant here. What is that constant? 2. Okay, who says 2? Who says 1/2? Who says 1? Who says something different? Pi? Pi is always a good guess. Okay, it's 2. Okay, 2Q. What does that look like? Q is a straight line, right? Q is a function of Q. And at 0, it's 0. And at 1, it takes on the value 2. Okay? That was the prior. This is the posterior. Right? It's a linear function. All right. We're making progress. What's the maximum likelihood estimate of Q? 1. Okay? You've observed 1 rainy day. Therefore, you believe it will rain forever. Okay, that's a caricature of maximum likelihood. All right. What is the predictive distribution? What is P of x2 given x1? Given x1 equals 1. That's a trickier thing. I'm not going to belabor it, but basically the probability of rain on the second day given rain on the first day, starting with this uniform prior, is the average of this thing, which ends up being 2/3. Okay? And by the way, the beta 2-1 answer was correct as well. That's just, if you actually know what a beta distribution is, that's an excellent answer. Okay. So it's all very simple. We didn't have to appeal to anything. And in this case, the calculations are very easy because we can compute the integral of Q between 0 and 1 to come up with the normalizing constant for it. Okay? Any questions about that? No? Of course, you know, if we observe many more coin tosses, in fact, maybe I'll do a demo now. Okay, what's going to happen? I don't know. Nothing. That's what happens when you run demos you wrote 15 years ago. Okay, I'm going to press the space button, see what happens. Oh, okay. So here are two Bayesian learners. One started with that uniform distribution. The other one started with a distribution that was more centered around 0.5. Okay? These are two Bayesian learners, and they're going to observe a bent coin. So they observe a tail. Okay, not a head, now a tail. All right. So this is the posterior for that guy. It's sort of just the flip of this because it was not a head, it was a tail. Okay? And the posterior of this guy moves a little bit. They still look different. Here is asymptotic consensus in action. They're observing the same data. 25 coin tosses. They look pretty similar, right? Okay? We can keep going. What is this approach, by the way? What does it look like? Huh? Yeah, this is a very vague question to which there are many answers. Okay. The shape of this density looks more and more Gaussian, and it's not a coincidence. It's because of the central limit theorem type arguments. Okay. So in these simple cases, the posterior will approach a Gaussian, and they'll approach each other, right? They're almost indistinguishable, apart from the fact that I'm rescaling, you know. Okay, everybody happy with that? So here is one possibly interesting lesson here. People worry a lot about the prior, okay? But actually, you know, if you have a reasonable amount of data, then, you know, as long as your prior isn't too dogmatic, as long as it doesn't give zero probability to places, you know, in parameter space that might actually be good parameters, then if you get enough data, you'll converge to reasonable parameter values, okay? And there is no such thing as a right prior. There is no such thing as nature's prior. You can come up with different, there's just like there's no nature's model, okay? You know, that basically you just have to represent enough variety of possible data generating mechanisms so that when you observe enough data, you can actually learn the model from that data. Any questions about this demo? No. Okay. All right. So so that was a bit of a boring boring exercise, but I think it's still useful just so you can see how this stuff works. So let's talk about some more interesting kind of modeling problems. So here's a classical kind of view of underfitting and overfitting in machine learning. Okay, so we are trying to do some regression. We're trying to model y's as a function of x's, and we could consider different models in this caricature just represented as different polynomials. So here's a constant polynomial fit to the data. This is a linear polynomial, quadratic, cubic, quartic, quintic, whatever this, sextic, you know, seventic, whatever. Okay? So now, well, clearly, well, here we don't know what's going on. There looks like there's some structure, but maybe we're underfitting by assuming a constant. Here, we're making ridiculous predictions between these two data points. We're predicting that the function shoots way up and comes back down. This smells like overfitting to us, doesn't it? Okay? We would like automatic methods to avoid both underfitting and overfitting. And I think we've all heard about regularization, right? So raise your hand if you know what regularization is. That's excellent. Okay, so let's see. How do we avoid overfitting and underfitting? Well, it turns out from the Bayesian framework, well, first of all, you know, we're not just interested in learning polynomials. Let's talk about some serious machine learning-y type problems. Well, you know, like finding clusters in data, how many clusters are there in the data, that's an interesting problem. Or, you know, doing dimensionality reduction, what should be the intrinsic dimensionality of that data? Or doing feature selection, or learning dynamical systems, or how many states to have in a hidden Markov model. doing source separation with independent components analysis, or maybe even learning the structure of a graphical model. Okay? These are all model selection questions, right? Model structure learning questions. So, do we need to invent new algorithms for solving all of these things? Well, not really, actually, because essentially the probability calculus, the sum rule and the product rule, gives us a way of trying to avoid both overfitting and underfitting. Okay? So let me explain that to you. This is kind of an important slide. This is the idea of Bayesian Occam's razor. Okay? Occam, William of Occam, we don't have an image of him either. He lived in the 1200s, I think, and he was a philosopher, and he said something in Latin that if you translate it into English, comes out to something like, don't come up with explanations that are more complicated than they need to be. Okay? So therefore, this idea of Occam's razor is very important in science. It says if you observe some evidence, try not to come up with an explanation for it that's too complicated. You should prefer simpler explanations. So regularization captures that, structural risk minimization, a lot of important frameworks in machine learning capture this idea of Occam's razor. So how does Occam's razor fit in within Bayesian statistics? Okay. So here's how. So imagine we're considering two different model classes, M and M prime, like a second and third order polynomial or something like that. Okay. Now, if we're doing model comparison, then we care about the posterior of our models given our data. And this term in red is the marginal likelihood. That is the probability of the data given the models. And by the sum and product rule, the marginal likelihood is the integral of the likelihood with respect to the prior. Okay? So that's just applying the mathematics. But what does it mean? Well, if I want to prefer a simple model, then maybe I should put my simplicity preference into this thing here, right? The prior, the prefer simpler models. But actually, it turns out, we can do that, but the marginal likelihood itself will automatically penalize models for being too unnecessarily complicated. So how does that work? Well, let's look at this expression here. This is the marginal likelihood. Here are three ways of interpreting this little bit of mathematics. Okay? This thing, by the way, is also called the model evidence or the integrated likelihood, and it has a couple of other names. Okay. So here's one way of interpreting this expression. It's the probability that randomly selected parameters from the prior would generate the observed data D. It's not the maximum likelihood. So clearly, if I have a model with more degrees of freedom, I can fit the data better if I'm going to optimize those degrees of freedom, right? So more complicated models will have higher maximum of this likelihood, but the marginal likelihood or integrated likelihood integrates the likelihood with respect to the prior. And an interpretation of that is choose parameters at random from your prior and see how often they generate the data. If you have a model that's too complicated, it can generate wildly many different things, and therefore the probability of it generating that particular data set might actually be lower because it's too complicated. Okay? And that interpretation is sort of given by this image here, okay? Where in this caricature, what we have is all possible data sets of some size n on this axis, and a model that's simple puts its probability mass on a smaller set of data sets. A model that's more complicated, that has more degrees of freedom, spreads this probability mass over many possible kinds of data. That's what it means to be a complicated model. Okay? But because this term here is a probability distribution over data sets, this has to integrate to 1, just like the green curve has to integrate to 1. So if you're gambling on a more complicated model, you're spreading your bets over more possible data sets, but everybody comes into this casino of modeling with a unit mass of money. Okay? So you can't win everywhere. You spread your bets more thinly, like this complicated model does. Okay? So that was the first interpretation, the probability that randomly selected parameters from the prior would generate the data D. Here's another interpretation. It's the probability of the data under the model averaging over all possible parameter values. That's just English for what that expression says. Here's an information theoretic view of this. Log of 1 over this marginal likelihood is the number of bits of surprise at observing data D under model M, where surprise is technically defined in information theory. Okay? The entropy is the average surprise. Okay. So, you know, a better model is one that is less surprised by the data. If a model is too complicated, then it will be surprised actually to see data that could have been explained by a simple model. Right? So, the hope is when you observe a particular data set, model classes that are too simple will be rejected because they're unlikely to generate that data, but also model classes that are too complex could generate many possible data sets, so you can also reject models that are too complex based on this. Okay? Any questions about this? Yep. You don't have to collect a lot of data. Here's an example with 8 data points. Okay? All right. So let's work through this example because it's the same example I showed before. It's the polynomials. So I have, 8 data points, these red dots, and I'm modeling the XY relationship. The blue line is the maximum likelihood polynomial of different orders. The green lines are samples from the posterior distribution of polynomials under some prior over the parameters of the polynomials. You have to choose, to be a well-defined model, you have to choose some prior. And for example, here what we're choosing is that the measurement noise is Gaussian with some standard deviation sigma, and the parameters are given Gaussian priors. The coefficients of the polynomial are given Gaussian priors. For those choices, I can do the computations analytically, and it's very easy. The basic picture will be similar for different choices, but obviously somewhat different. You know, if I vary the prior wildly, I'll get different choices, sort of different pictures coming out here, but the basic phenomena are still there. All right, so what are the basic phenomena here? The basic phenomena are that if I were to compute the marginal likelihood for these different models, here it is, there are 8 different models from 0 to 7th order polynomial. This is the marginal likelihood normalized, just to rescale the axis. And essentially what it says is based on these 8 data points, 0th, 1st, 2nd, and 3rd order polynomials seem reasonable, and these are actually a bit too small to see on this plot. So it's actually rejecting these complicated models. If I change the priors around somewhat, I will get the same sort of effect where it tends to reject models that are too complicated, but I can manipulate the priors in interesting ways so that instead of seeing an Occam's, I call this Occam's hill, okay? It's peaking at a particular model. Instead, I can tweak the priors to get Occam's plateau, which goes like this, which is interesting. We have Carl Rasmussen and I have a paper called Occam's Razor about that. Yeah, this is consistent. Yeah, I mean, BIC is an approximation to this. Okay, there's no justification for BIC other than I can't do my integrals analytically, so I'm going to use BIC instead. And I'll explain that in a few slides. Okay. Yep. No. Okay. So here I'm just computing the marginal likelihood for these 7 different models. I would multiply that by a prior, which might say I like odd numbers or something like that. You know, your prior could be anything, right? And that would just rescale these bars. All right. So the marginal likelihood is independent of the prior over model orders. So let me do a demo.
Maybe one question.
Yep.
So then just looking at the P of y given m, are you happy with taking there the maximum, or would you then prefer to define this P of m as well? I mean, if the P of arbitrary thing there was the same one.
Yeah, I'm not happy with taking maxima in general. I mean, in general, what you would like to do here is, if you can computationally afford to do so, average the predictions of all the models that you've considered. But the average of these guys will have such small weight that we can effectively ignore them. But we should probably average over these 4s when we make predictions. These 4 when we make predictions, because they all have significant mass. Yeah. Okay, let's do this demo. Polybase. Okay, what happened? All right. So here's a different data set. All right, different 8 data points, and you know, it's again saying 0th, first, and second order polynomials are good, but you know, it gives a little bit of mass on these guys. In fact, I can run this again. It'll generate random stuff every time. I think. All right. So here's maybe slightly more interesting. I've generated, again, a bunch of data points in red, and I've plotted. Now it really thinks that constant is probably the best model. Seems reasonable. Okay. And I have here the log marginal likelihood. So you can see that there is a tail, it's just going down. Okay. Okay. So I'll get back to this. All right. So so now I'm gonna go through. Okay. So this was, you know, just an exercise in doing Bayesian inference. Now, for decades, people have thought about this question: how do you choose your priors? Okay. So I'm going to give you a kind of survey of different ways of choosing your priors. And then I'm going to do a little exercise, and then I'm going to have a tutorial on how to choose priors. Okay? Actually, yeah? Yes, question from the other room. Yes, question from the other room.
Hi, can you hear me?
Yes.
Oh. Yes. Yes, you can hear me. Okay, I've a question. What happens if none of the models that you consider is actually very good? Is there any way of guarding against picking a completely useless model?
That's an excellent question. From the invisible voice. In this setup that I've described, if your data comes from not a polynomial, for example, then you will do as well as you can in the limit using polynomials. So you'll converge to kind of the maximum likelihood, just like you're doing maximum likelihood, you'll converge to the best model in a KL sense, but you're living in a closed universe of up to 7th order polynomials, okay? Now, that should make us uncomfortable, and so the way we deal with that is we open up our universe a bit more. And so the whole point of Bayesian nonparametrics, which I'll cover in my subsequent lectures, is to try to open up our universe so that we are not stuck in the situation where our models are too simple to capture what's actually happening there. So we'll do as best we can with the polynomials that we have. And there is no way within our universe, using purely the Bayesian machinery, to tell whether we're doing well or not. There is a lot of work on doing model diagnostics afterwards to see whether it's sensible or not, but it doesn't come from the basic Bayesian framework. Yeah. All right, so let me move on. Okay, so how do we choose priors? So there are different schools of thought. There are a lot of people called objective Bayesians. There's a sort of sub-community of Bayesian statistics called objective Bayesians. So in a slight abuse of the terminology, I'll say that what they're doing is they're coming up with objective priors. And these tend to be non-informative priors that attempt to capture ignorance and have good frequentist properties. Okay, so these are algorithmic ways of coming up with priors. All right, and I will, in a few slides, I will describe some of the basic ideas in objective Bayes as well. All right, then there is subjective Bayesians. Subjective Bayesians say priors should capture our beliefs as well as possible. Although they are subjective, but they're not arbitrary, right? Because your beliefs about any particular domain aren't arbitrary. You can't just choose anything because it won't capture your beliefs, because you wouldn't be betting with those beliefs, right? If you're not willing to bet with those beliefs, then that's not your beliefs, okay? All right, so that's subjective Bayesians. And then, not mutually exclusive thing is using hierarchical priors, where you have some model and you put priors on its parameters, and those priors have hyperparameters, then you put priors on those hyperparameters, and so on. So there are multiple levels, but people often think, oh, there is an infinite recursion here, but that's rubbish. Okay, at some point, essentially all your models are making predictions about data. You could add extra levels above if you want, as much as you want, but then you can just integrate those levels out, and that just corresponds to different predictions over your data. So there is no infinite recursion here. You just go up to whatever level that makes the predictions about the data that you think are reasonable. And then there is empirical Bayesians, where essentially they learn some of the parameters of the prior from the data, either by doing some kind of maximum likelihood over those prior hyperparameters, or by computing some moments of the data and using those to set the prior parameters and so on. Okay, so these are different schools of thought. Here's just a little bit about objective Bayesians and non-informative priors. So consider a Gaussian with mean mu and variance sigma squared. The parameter mu informs us about the location of the data, right? It's kind of called a location parameter. Sigma is usually called a scale parameter. So if we pick the prior p of mu to be the same for any translation of mu, then predictions become location invariant, which sounds great, okay? But there's a little bit of a problem. If p of mu is p of mu minus a for all a, then that implies that p of mu has to be something like, loosely speaking, a uniform distribution with between minus infinity and infinity. We can approach that limit in different ways if we want, but that's an improper prior. That prior does not, it can't be integrated to 1, okay? So similarly, sigma informs us about the scale of the data, so we could pick p of sigma to be 1 over sigma or something like that, okay? So the problems are, it's hard or impossible to generalize these ideas to all parameters of a complicated model. if we choose these kinds of improper priors, then we risk incoherent inferences. So basically, the rules of probability theory break down. For example, this iterated expectation rule will not necessarily hold if we choose improper priors. We get paradoxes. We might get improper posteriors. It's a bloody mess, okay? But there's like a whole conference of people working on this. Because it's a mess, there's a lot of work to do. Okay, so it keeps people in business. All right. So here's another way of coming up with objective priors. These are called reference priors. This is quite an elegant idea, actually, I think. So it captures the notion of non-informativeness. So given a model or likelihood function, p of x given theta, we wish to find the prior on theta such that an experiment involving observing x is expected to provide the most information about theta. So this is an information theoretic way of coming up with priors. So why does this make sense? Well, if observing x gives us the most information about theta, that says that most of the information about theta will come from the experiment rather than the prior. So it's a way of making the prior most sensitive to the data itself, okay? So how do we measure the information about theta given by x? Well, we look at the change in entropy. So before x, before observing x, we had an entropy on theta given by our prior. After observing x, we have a new entropy on theta, which we have to average over all possible values of x. And this change in entropy is the amount of information that x gave us about theta. That's a basic definition of information, is the change in entropy. Okay? So reference priors, what they do is they try to maximize that change in entropy as a function of the prior. And this can be generalized to n observations. Now, it's a beautiful idea if you're going to be objective. It's very hard to compute this stuff in general. And the prior depends on the size of the data to be observed. So the reference prior for n data points is different from the reference prior for n plus 1 data points, which seems weird from the point of view of, well, you know, where does the prior come from? Okay. 5 minutes. Does that leave me time for questions as well? Okay, good. All right, excellent. All right. That's the idea of a reference prior. Very neat idea, but, you know, has its own problems. Okay, here is another very well-known form of objective prior. This is called Jeffreys prior. It's motivated by invariance argument. So the principle of choosing priors should not depend on their parameterization. So instead of choosing a prior, imagine I chose a prior on theta, okay? And now I'd like, you know, I'd like basically to think about possible ways of reparametrizing theta. Let's say I parameterize theta in terms of phi. I take a logarithm or I do some other one-to-one reparameterization. I don't want my prior to be affected by that reparameterization. And, you know, I won't go into the details, but essentially Jeffreys prior says if I choose my prior to be proportional to the square root of the Fisher information, then I'll get some nice invariances in here. Again, it's hard or impossible to generalize to all parameters of a complicated model. You know, good luck coming up with a reference prior for, you know, your, you know, deep neural network or something like that, you know, or your Jeffreys prior for your deep neural network. It's just not going to happen. You risk incoherent inferences, paradoxes, etc. Subjective priors. So priors should capture our beliefs as well as possible, otherwise we're not coherent. Well, how do we know our beliefs? Okay, well, think about the problem domain a little bit. Generate data from the prior. Does it match our expectations? You know, that's the way you think about your beliefs. Even very vague priors can be useful in this setting because the data will concentrate the posterior around reasonable models. And the point is the key ingredient of Bayesian methods is not the prior itself, it's the idea of averaging over different possibilities. Okay? empirical priors. So here we consider a hierarchical model with parameters theta. And we say, okay, let's estimate the hyperparameters from the data. So essentially, the prior itself has some hyperparameters alpha. Hyperparameter is just parameters of a prior on the parameters of a model. Okay, you can have hyperparameters if you want, right? So here is something you could do. You could estimate these alphas from the data, you know, and then when you predict, you just plug in those alphas. It's nice and robust in some ways because, you know, you can estimate scales and things after you've observed the data. But, you know, you're double counting the data because you're using the data both to estimate the hyperparameters and then to make predictions. So there's a small risk of overfitting when you do this, and sometimes a large risk if you do this carelessly. Okay. Okay, I want to get to the exercise. How many minutes do I have? 0-ish? All right. Okay, there is exponential families and conjugate priors. I'm going to skip this because it's a bit too much math and a bit boring right now. I can come back to it after lunch. But we're going to do an exercise. Okay? So, all right, get your pencil and paper out. Consider logistic regression. Okay, logistic regression is one of our favorite models, one of the most widely used in industry. It basically is a way of doing binary classification from some inputs x with some weights and some bias b by just saying the probability of y being 1 is 1 over 1 plus e to the linear function of x. Okay? That's good old logistic regression. Now, logistic regression is also nice because of this footnote that you can't see. This is like a typical neuron in a circa 1980s neural network. Oh, sorry, circa 2013 neural network. Okay? So, you know, these neural networks are composed of a lot of little logistic regression units. Okay? So, you know, seems like a useful exercise. Well, how do we choose priors for logistic regression? Assume our data is binary. So our x's are binary, d-dimensional. How should we choose a prior? As a simple exercise, I'm going to focus on the case where I'm going to choose Gaussian priors, and the only thing I'm going to ask you to think about is what happens as we vary the variance or standard deviation of that Gaussian. Okay? So this is the Gaussian on the W's, and there's a similar same standard deviation Gaussian on the bias B. And we'll do the first exercise, and then we'll take some questions if we have time. Okay? So the first exercise is for d equals 1, okay? One input, one binary input, and one binary output, logistic regression. What happens if we choose a very high variance, so sigma being much, much larger than 0, as a non-informative prior over W and B? Okay, so talk to your neighbor for 2 minutes. So try to imagine what happens if you... Okay, what happens to the model? Yeah, what happens to this quantity p? Okay. All right. I had a good question, which was what happens to what? That was a very good question. You know, What I meant is what happens to the model, like what kind of predictions does the model make? And so who has some? Okay. Ah, interesting question. Yeah. Are you thinking about what happens after you observe some data and you learn from it? Yeah. Sort of, except, you know, you're not doing map inference. You're supposed to be averaging over the parameters. But yeah, I think you're right about that. But I was fishing for something different. What happens? What does the model predict about data? Okay, so does somebody else have? But you're not wrong. I think you have a very good insight there. Yeah. Whatever was the input, the output will be 50%. Who agrees with that? Okay, who disagrees with that? Okay, somebody who disagrees. You over there who disagree. Is less likely to be a half. So what will the output look like? What will the probabilities look like? Okay. I think this is great. We're going to leave this as a cliffhanger, okay? So you know, I've never heard so many people go, oh, when they know they're about to go for lunch. But we'll leave this as a cliffhanger. We'll come back to it in my next lecture. Okay.